So last class we have completed with the binary tree. So what is binary tree? And traversal, we have completed the three types of traversal: in order, pre-order, and post order. So again, this all three come under, and one more different type of traverse is that level order. All these come under category of two types. It is broadly classified into two types. One is breadth first traversal, and the other is depth first traversal. Okay, so in case of depth first, it goes deep into the leaf node. From when you start from root node, it first visits each and every of the node, but by how it will traverse is that it reaches the deepest node. So in such a way that it will traverse, you will visit the node. In case of level order, it is coming under the breadth first. If breadth first is that you will visit the node by each and every level from left to right, you will visit. That is called breadth first search. And the depth first is that you are visiting the each and every of the deepest node. Then you will go from left to right. That is what the depth first search. And we have seen many types of how we'll, even we have seen the expression tree also. From the given expression, how we are going to build the tree. Okay, for the given input, if it is like a pre-order, if they are given the prefix expression, okay, how we are going to form a expression tree. Okay, and you know what are the properties of expression tree. So you have to know all the different types of trees. Okay, in case of third unit, you have to know all the types of trees and what are the properties of a tree, that you have to know. Okay, so up to binary tree we have seen, and also the expression tree. And next is that how we are going to build a tree, binary tree, from the given traversal pairs. Okay, for example, you take this. Okay, to build a binary tree, you require any two type of uh, traversal, either in order and pre-order, or in order and post order, and in order and level order. For every type of given traversal pair, you need in order. Okay, so how you are going to build? For example, they will give in order expression, in order traversal uh, expression, and the pre-order traversal expression. From this given input, you are going to build a tree, building binary tree. Okay, but to build a binary tree, you need at least two pairs. That's what I mean, not two pairs, two traversal. That's what we are calling it as a pairs. Okay, two pairs, two traversals. Okay, please stop chatting. Please stop chatting, and each and everyone is chatting with me. So stop typing your registration number. I can come to your know your registration number from the report. So please stop chatting and listen. If the pre-order traverse is given, okay, for example, so from the pre-order you come to know that in case of pre-order, you will visit the root node first. Okay, whenever a traversal is given, an traversal order is given, you can easily come to know that the first node is the root node. In case of post order, you can come to know the last node is the root node. Okay, and once the in order is given, what happens? Once the root node is identified, from the given pre-order or a post order, okay, all the nodes in the left subtree, okay, and right subtree of the root node can be identified using the in order. Okay, that we go through an example that will show in clearly with an example. For given pre-order and post-order traversal, for example, binary tree can be obtained uniquely. So this is an example I have taken. You're going to construct a binary tree, okay, from the in order and the post order. So this is very simple. Next, I have to move on to the major topic, is that binary search tree. One of the type of the binary tree is that binary search tree. It is an application of binary search tree, binary tree. Okay, so we'll complete with this example as much as quick. Okay, from the post order, post order sequence. See, from the post order sequence, okay, I can come to know that what we told, the A is the last node, is the root node, that you know. Okay, the previous nodes, all these nodes can be what? The internal nodes. Okay, we know that internal root node is also called as internal node. From this expression, we can come to know that A is a root node. That's what I have highlighted with red font. Okay, then from the in order, once I know this A, okay, I know where it is A. I am taking the in order sequence. In order, I am finding the letter A. I am finding the node A. Okay, once I find the node A, I can, since it is in order traversal, I can split this tree into two parts. One is left part and the other is right part. So this A becomes the what? Root node. This A becomes a root node from this given post order. Okay, so that's what I'm classifying. That's why I'm dividing this in order sequence into two part. One is left and the right subtree. So this is called left subtree and this is right subtree. Okay, I'm making a tree now with this A. Okay, I can come to know that DGB is what? Left subtree, and HEICF is a right subtree. Okay, fine. Next, next again, what should I do? Once I complete it, again I will take the left subtree now. Okay, left subtree, and I have to find the root node for this given subtree. And the same thing, once I completed this one, I'll go for this other one. Once I completed this, I'll go for the right subtree. So now let us go for the left subtree. From the post order sequence GDB, the root of the tree is B. Okay, so DG from the GDB, when you take this, okay, once I find this DGB, okay, I am considering this one GDB. I have to take this post order sequence. Okay, I know these are the in order sequence. Then I am taking these values when comparing with the post order. Same GDB, I come to know that this among three nodes, B is the what? Root node, because this is a post order. So I'm making B as the root node. Okay, remaining is that what? DG. How we are finding, how we are telling this is going to be the left of the B, not the right. Not the right. From the in order sequence, we come to know. From the in order sequence, DGB is what? So once we find that B is what? Uh, Root node. Okay, you know that in case of in order, this is, one second, I will make it as a red font. Once I find this, okay, this B is what? Now the root node. So when I take this sequence DGB, so we know that how is the travel, how will you traverse from in case of tree, in case of in order. First I will complete the left subtree, then I will go to the root. So this is what I'm building, that I'm telling that this DG is the left subtree. Left subtree. Then again, from the post order sequence, I come to know that GD, okay, the root of the tree is D. Okay, once I find that GD is that root is, the root of the tree is D. So I concluding that D is the root node. And again from the in order sequence, okay, so DG is what? In order sequence. In order sequence, I come to know what? DG. Okay, I found that this is what? I found that this is the root node. I found this is the root node now. So I'm considering this sequence DG. I come to know that there is no left part. Okay, D, since D is the root node, and there should be what? A right node is there. Right child is there. So G is the right child and D is the root node. There is no left child. So this is how we are building the this left subtree. The same way we are doing for HEICF for the right. Once I complete this, okay, then I will move to the right subtree. The same way you have to do it for the right subtree. So you have to follow the algorithm. Okay, once you follow the algorithm, you try to implement, take this homework and try to implement. Draw a diagram. Okay, take an expression, take the given expression and build a tree. Okay, we'll finalize with this uh, type of I mean the building a tree. Okay, like that you have, we can develop, you can build a tree based on this in order, post order, and in order and level order. So building a tree, binary tree from the given traversal path. Okay, next we'll move to the major topic, binary search tree. Okay, so binary search, we have seen binary tree. What is binary search tree? Okay, when you take the binary search tree property, okay, whenever you are creating a tree, whenever you are creating tree, you will insert the node in terms of some condition. With the condition only you will insert a particular element into the tree. What is the condition is that the left subtree of a node contains only nodes with keys lesser than the nodes key. For example, when you take any of the node in the binary search tree, for example, this is a binary tree. When I will tell this binary tree is binary search tree. Okay. For example, you take this node 8. Okay, this is a key. For our simplicity, we are taking only the unique node. We are not taking the duplicate node. Don't take that another, you are trying to insert another element 8. Okay, we are taking, for our simplicity, we are taking only the unique element, unique key. When you take this key 8, okay, look at the left child. You know that only two childs you have for a binary tree. Okay, so look at the left child. In case of left child, it is lesser than the given key. Okay, lesser than the root element. So when you take 3, this is lesser than the root element. When you take 10, okay, this is greater than the right element. Okay, greater than the root element. For example, you take this scenario 647. Okay, I consider, I am check this 4. Where is this 4? It is lesser than the root element. So 6, uh, here 4 is lesser than the 6. That's why the 4 element 4 is placed to the left of the key 6. What about the key 7? That should be placed at the right position, right? That should be the right child of the key 6. Okay, so that is what the condition is, that the left subtree of a node, okay, the left subtree, this is the left subtree of a node is always lesser than the root node, and the right subtree is always greater than the root node. This is the condition you are going to follow. Okay, the left and right subtree each must also be a binary search tree. You need to take this again this subtree. Okay, you take this again, this is a subtree. For this subtree, who is the root node? 3 is the root node. Okay, for this root node, okay, it consider, check the left child. When you take the left child, it is lesser than the root node. Now this 3 is acting as a root node for this particular subtree. Okay, 1, whatever the key 1, it is lesser than the root node. Okay, when you check the condition, when you check the condition for right child, you take this 6 is greater than the root element. Okay, this is how this the last point refers. The left and right subtree each must also be a binary search tree. Okay, the condition is that when you, the left child is always lesser than the root element, the right child is always greater than the root element. That is the binary search tree. So what is the benefit of this? What is the advantage of this? When I try to search an element, for example 6, what is, why we are move why we, what is the advantage of this binary search tree? When I try to search an element 6, okay, instead of searching each and every node, the whole tree, what I will do, I will directly check whether the given element is here 6 is lesser than the root node. Once it is lesser, if it is lesser, I will move towards this side, left side. I don't want to search for the right side. Okay, I don't need to search the whole right subtree. Okay, it's a waste of time. Okay, so what I will do go directly to the left child, left subtree. Okay, once again I will come here, I am checking the 6, this it is greater than 3 now. Okay, then I will not go to the left part. If the left child is having, if the left side is having some 50 nodes, for example, you consider if you have uh, left subtree of 3 is considering having a 50 nodes, I no need to check for the whole 50 nodes. Directly I will move to the right subtree. Why? Because the 6 is greater than the node 3. I'll go directly to this. So wasting of 50 seconds, for example, searching a node, it takes 1 second. So 50 seconds is wasted here. Okay. So this is the advantage of the binary search tree. Advantage of the binary search tree. The binary search is that it's reducing half of the time. Topic. So what are the operations? As like linked list, as like any type of data structure, you have the basic operations, right? Insert, delete, right? In apart from this, you have some operations. Okay, we told that traversal is there. Okay, I can, this, since it's a tree, I can able to visit each and every node. Okay, so when I take traversal, there are 3 types of operation. Okay, so what are the operations in binary search tree? Insert, delete, search. If you want to find an element, is there or not? Okay, so I need to search any key is there in the tree or not. So that is called search operation. Is there a same thing is there in the linked list, stack is there? If you want to find an element is there or not, you will go for the search operation and find a minimum. I'll tell. Find minimum. What is it? For a given tree, for example, for a given tree, I need to know which is the minimum element. Sorry, minimum key, or you can say minimum element also. Okay, in this tree, the one is the minimum element, minimum key. Okay, if we want to find, okay, so the find operation, find minimum operation will go directly to the left subtree. The find maximum operation will go directly to the right subtree of the root node. That is how it works. The find minimum operation, how it will work, it go directly to the left subtree of the root node. Find maximum is the operation where it goes directly to the right subtree of the root node. Okay, display, again display and traversal also same thing. Both are same only actually. See, if I try to display, if I call display function, again, how will you want to display? Either by pre-order, in order, or post order. Okay, fine. Next, before getting into the traversal or different types of operation, I want to make it clear there are 2 types of uh, traversal in an algorithm, in a given tree. One is recursive. I hope this is basic one. You all know these things. Recursive binary search, okay, and iterative binary search. Okay, for this simplicity, I have taken example factorial. Okay, a program is called recursive when you are calling this program is recursive when an entity calls itself, it is calling its own. When it is calling its own function, then you call that particular function is called a recursive function. For example, here this factorial using recursive, what is the function name? Okay, when I go into this function, when I get into this function, it's calling the same function. Factorial using, again it's calling, this is called recursive. Okay, here a program is called iterative. When you are calling a program is iterative, when there is a loop or repetition, you use like for loop, while. Okay, any of the loop you are using, that you call that kind of program is the iterative. The same thing, you can write an program, you can write an algorithm either using recursive or iterative. If you want to traverse a tree, I can use either recursive or iteration. Okay, and one more thing, the disadvantage, there is a disadvantage between recursive and iteration. When you take recursion, the lines of coding is simple. Lines of coding is simple, but it takes more space. It takes storage space. When you consider the storage space, it takes more memory. Okay, that's the disadvantage in case of recursion. But LOC, lines of code, is simpler. Okay, and it has its own advantage and disadvantage. Iteration. Okay, we'll in case of our binary tree operation, we'll mostly consider the recursive type. Okay, we will use only the recursive binary search. Okay, and next is in order predecessor and in order successor. Okay, I'll make it clear. In order predecessor and in order successor. What is in order predecessor and in order successor? For a given subtree, keep in mind, for a given subtree, for a given node, for example, for a given node, you will tell that the highest element of the left subtree is called the in order predecessor. Keep in mind, highest element, highest key of the left subtree is called in order predecessor. Okay, then you come to in order successor. Lowest element, lowest key in the right subtree of a given node is called the in order successor. When you take this for a given node 25, okay, for a given node 25 or the root node 25, this is the left subtree, this is the right subtree. I am checking, okay, the highest element here is 20. So I say that the in order predecessor for a given node is 20. Okay, and the in order successor for a given node 25 is 35. How I say 35? Because this is the lowest key in the right subtree. So you make it as vice versa. For left, it should be highest. For right, it should be lowest. Why I'm telling why this is you when it will be used in, because traversal will be useful, or deleting a node. If you want to delete a node in a tree, for example, you take this tree. Okay, I want to delete an element 10. I want to delete an element 10. In that scenario, this in order predecessor and in order successor are used. There only it is required. Okay, so but you have to know what is in order predecessor and in order successor. For example, if I am deleting 40, I am deleting 40. Okay, there I require again what for the given node 40. This is what left subtree and this is right subtree. Okay, for a given I'm considering 40 as a given node. Okay, that for this scenario I'm taking 40 is the root node. When 40 is the root node, left subtree is what 35, only one node it has, and right subtree is it consists of three nodes. Okay, so this is left subtree and this is right subtree. And what is the in order successor for the node 40? What is the in order successor for the node 40? I have to search for the lowest element in the right subtree. The lowest element is 44. I say that 44 is the in order successor of the given root node 40. Okay, fine. In algorithm for the binary search tree, you know that there are different types of operation. So we'll see one by one. The first is what? Insert. So I have pictorial representation I have shown. This is the at particular stage, this is the given tree. If I want to insert element 8, you know that I have to check for from each and every node. Okay, when I take 8, okay, I'll go with what? Check with root node 5, given node 5. Okay, so it is greater. I will come here. Okay, I will come to the right side. So because this is the root node, I will come here. Okay, again 7 I will check. It is lesser than or greater than. Yes, it is greater than the 7. So I will go to the right side. I will make this 8. I will insert the node 8 at the right child of the 7. That's all. That's what is shown. Next, for example, I am going to insert 3. Okay, this is the current uh, stage of the tree. I am going to insert 3. What I will do? I will check with the root node 5. Yes, it is lesser than 5. Okay, I will move towards the left subtree. Once I move here, okay, I will check again. I will consider this as the root node. I will take this as the root node. I will check what greater than or lesser than. So the given key is what? 3. Okay, so it is greater than. So I'll make this 3 as the right side of the 1. So that's what I made here. Okay, so this is how we are inserting. This is fine. How we are going to make convert it into coding, that is important. So first I will check if node equal to null. If simply if there is no nothing is there, if the like node is not there, what I will do, I will create a node. So if I want to insert, okay, if there is like there is no node in the tree, there is no node in the tree, there is no elements in the tree, what I will do, I have to create a node. Okay, if for our scenario there are nodes in the tree, so what I will do, I will go to this part. If data root data, if it is there, what I'll do, I'll insert at the right. Insert, I'll call the function insert. So this is the recursive uh, binary search. Why? Because we are calling the insert function again, it calls directly the same function. Okay, again here if it is lesser than, here this is data is greater than, so this is important. Before it was arrow operator. Why? Because given data is what, 8. Given data is 8. If it is greater than root of data, okay, what is root of data? Root of data is 5. This is 5 now, which I highlighted is 5. This is 8. Data is 8. Given data, so 8 greater than 5. Yes, true. We have to move to the right side. I'll show in pictorial representation and code also, don't worry. If it is lesser, data is lesser, for example 3 lesser than 5, so this code enters. Okay, this is a recursive binary tree. Why? Because the insert function is keep on calling. Why? Because what, you have another node in the left or right child in the tree, that's why it's calling insert function. Okay, don't get shocked with this code. Okay, I'll take this insert function alone. I'll take this insert function alone. I'll show you clearly. Okay, so this is the, for inserting a node, for inserting a node, how many arguments are required? How many arguments are required? It takes 2 arguments. Okay, one is the root node, one is temporary node. Okay, we'll check. So how it is happening? For example, this is what type def is the structure of the tree that you know. This is the left subtree. For left subtree, this is the right subtree and the data. Okay, and these are the functions in this program: create function, insert function, pre-order function. This is what a pre-order traversal. Okay, fine. This is in main. Come to the main function. I have highlighted all the functions in red font. So this is a root node. It's a root pointer. Basically it's initialized as null. Okay, then you are going to do part. So initially you are doing what, temp create. I'll show in the whiteboard. Okay, what is this? Temp equal to create. So automatically it calls the create function. It comes over here, it comes to create function. Okay, what it returns? Temp. It returns the address of the created node. Okay, that this I have seen many times. Okay, and this also data is created, scanf we have put some data 50, and we have made the left and right child as null. So what is there? So here it is 100. This is what? Null. I'll make only n. I'm not putting the whole null. We know the address. Let it be 1000, and we are stored in the temp. That's what create function returns 1000. That 1000 is stored in the temp. Okay, fine. Next, if you are checking if root equal to null, yes, it is null only, because now only you are creating a tree. Okay, now only you are creating a tree. Yes, root initially it was what? Null. We are shown here, no? Root is null. I'll root. Okay. Null. Then what you will do, if it is root is null, then this is the first node. Whatever the node creator, this is the first node. So that's why you are passing the temp address, temp value to the root value. Okay, so temp value to the root value. What's the temp value? 1000. So it is passed to the, now it is pointing, root is pointing to 1000. Next, else. Okay, this is okay if, because this is the first node created, only if only works. It won't goes to else part. It won't goes to do now is executed only the if condition. Okay, else will not work. Else will not, right now it won't work. Okay, now what happens? It goes to the, directly goes to the what? One second. So this else will not work now. Where is this else? This, okay. Under the else you have what only one line. Okay, next what is asking? So this else is not working. That's all. Okay, next what is happening? Print, do you want to enter more element? If you are printing yes, I want to print more element. You are getting the get character. I am pressing yes. Why I am pressing yes? That y is catched. Okay, scanf. Then you are checking yes while you are condition checking y. If it is like a small y or capital Y, this is the condition. Okay, if it is small y also, if it is capital Y also, it will take. That's why I'm using or operator here. Okay, it can take any of the condition, small y or caps Y. Okay, what happens if it is true? You are pressing that that I want to insert one more element, one more node into the tree. So that's why I'm pressing Y. What happens now? The while becomes true, it again goes to the do part. It again goes to the do part. Now this do will work again. What happens? So once it comes to the do part, what is create function? It again it's calling create function. The address is stored in temp. What happens? I'll show it. It creates. It creates one node, right? Create function is to create this node. That's all. It is having some value. As of now, it is null. Okay. This is having, like, let it be 50. This is null. Okay, and what we are doing, you are passing the address to the temp. It was already 1000. Now it becomes what? Okay, this is what happening. So now this temp is created. So it created new node. Again, you are creating. If root equal to equal null, no, at this condition, the root is not equal to equal null, because it is having some element. Okay, this if will not work, it goes to else part. Okay, what is else part here? Else is calling what? Only one line. Under the else you have only one line, that is insert root temp. You have taking two argument. I'll make it as large. It taking two argument. One, you are sending first argument as root, and the second argument is temp. Nothing but root is what here? Root comma temp. Okay, root is 1000 comma temp is 2000. That's all. These two values, two arguments, 1000 comma 2000 is passed to the create insert function. So this is the insert function. Please stop chatting. I know your attendance. Please stop chatting and listen. It gets disturbed for me. That's why. So root is what? 1000 and temp is 2000. So you are coming here. What you are checking? If data temp tends data is what? Temp tends data is temp tends data is what? 50. Okay, 50 lesser than root tens data. That's all simple. I have to check this condition. If temp tens data is 50 lesser than root tens data. Data is, this is what data, you know. This is data part, middle one is data part, and this is left part, and this is right part. So root tens data. Okay. So what I'm doing, if it is lesser, I'll go inside. If root left not equal to null. Okay, so I have to go to which side? If it is lesser than, what I am checking first for the root tends left not equal to null. Is it not equal to null? This root tends left not equal to null. So this is what? False. It is equal to null. Okay. So what happens? So it goes to else part. Okay. What I am doing? Temp tends. I am passing the value of temp to the root left. That's all. So root left is what? Root left is this one. This one. Root left is this one. I have to pass this temp over here. So temp is what? $2,000. Okay, that's all. Now it is pointing to what? I'll make it clear. $2,100. This is null. Okay, this is null. As of now, it is null. How it is becoming the left child? It's checking with the data part. Once it is left as what? Once it becomes a left child, okay, it is again what checking with the left child. Sorry, root left data field is checked whether it is null or not. If it is null, what I have to make this as the left child. That's why I'm passing the root node. That's why I'm passing the root node. So now it is pointing to left child. Now it is pointing to left. That's all simple. This is how you are inserting a node into the tree. For example, you are inserting 150. What happens? I'll check with the same condition. If it is 150, what happens? It goes directly to this. If you are passing like 150 is created, how it is happening? You know that it calls a new node is created using the create function. You all know these things. A new node is created, and this address, a new node address is stored in this temp variable that you know. So let it be 3000. So you know that the address is stored. So let it be, I am considering that 150. So 150, as of now it is null, null, this is null. Okay, so you know that once it's created, we are passing the address of the newly created node to the temp. Okay, so but now I am passing what, when I am calling the insert function, I will pass 3000 comma 1000. So for example 1000 comma 3000 based upon the input argument, based upon the argument it calls. Now what is called root is what, 1000 comma 3000. So 1000 comma 3000 it coming, it's coming. So 10 data, 10 data is 150, 150 lesser than 100, it is false, this will not work. 100, sorry, 150 lesser than 100, so this will not work, if this if part will not work. So under this if we are having two statements, condition if else. Why this is for condition checking whether it is lesser than root. Once it is lesser, what is the necessary of this, means that is whether the left field is null or not, that you have to check. For this only you are using this highlighted if else. Okay, fine, you know that it is false, it goes directly, it's checking. And I told you don't take the duplicate element. Don't, for our simplicity we are considering, we are not considering the duplicate keys, you are taking only the unique key. Then you have to go for equal to that, checking the complexity of the code increases. Okay, that's why I'm telling you take only the unique elements. See here 150 greater than 100, yes, true, fine, it goes inside. Once it goes inside, what I told you have to check for the right field, you have to check whether the right field is null. If it is null, make that the created node, make, you are going to insert that node to that what, right part. Okay, so now it, according to this what, not equal to null, yes, it is false now, actually it is null, so this will not work now, this will not work. So it goes to else part. What I'm doing, I'm making this as what, replacing the temp to root tens right equal to temp, that's all. Root tens right equal to temp, it's meaning that I'm taking the temp value and assigning it to the root tens right, that's all. 300, 3000 is address. So based upon the address only we are pointing to each and every node. Now it becomes okay, fine. For example, we will take one more thing, 75. Oh, you know that when 75 where it will come, it comes here, it has to come the right side of the node 50. Okay, that you will check. And you know one thing what, you know that in new nodes created, okay, based upon the create node function. I'll erase this, as of now we'll erase this, it's not now pointing. Now we are going to insert a node 75. What happens, so a new node is created. Let I am creating here. Why? Because it is easy to draw, that's why I'm creating here. Okay, so 75, 75, this is null, null, this is null. Okay, and this address is where it is stored, this, let it be 4000, 4000 is stored in temp, that you know. Okay, fine, so it is now the temp is pointing to the particular node, so I didn't include, I didn't insert this node. Now what I will send to the insert function, 1000 comma 4000, 1000 comma 4000 I will send. So 1000 comma 4000 it will come here, it will check. Temp dense data is what, 75, 75 lesser than 100, yes, true. 75 is lesser than 100. Okay, so it will come to this left child. Once I come to this left child, it's going to be inserted the subtree. Okay, fine. Next thing what I'll check, I check for this root tens left field, whether it is null or not. Okay, it is not null, it is not equal to null, so this if condition will work now, this if will work now. Before that, if it is left is null, this will work, if it is not null, this if will work. Okay, what is happening here? Again, it's calling insert function. This is what recursive. It's called recursive function. Again, this what has happened? This root left. You know that left insert function will require what? Insert function require two two arguments. Now this root left is considering acting as what? Root. Keep in mind, what is the root left value? What is the root left value? 2000. This 2000 is now acting as a root. Now I will pass 2000 comma 4000. Okay, I am not passing 1000 here. This is acting as a root now. 2000 comma 4000 I will pass. So 2000 comma 4000. It comes here. Again it comes in. Okay, it's checking. So now what? 2000 is pointing to this one, right? 2000 is pointing to this one. So I come to know that what? Root tens data. So root tens data is not like this 100. Now this is the root node. 2000 is pointing to this one. So root tens data is not 50. So you have to think in this way. Root tens data is 50. I have to check with the temp tens data. Temp tens data is 75. 75 lesser than 50. If it is lesser than 50, no, it is false. 75 lesser than 75 lesser than 50, it's false. Okay, it has to go. It has to go this. This if will not work. It has to go this if part. It means that it has to move to the right part. That's all. So again, I'm checking. For example, simplicity. If I'm checking, you can use this instead of if you can use else also. You can put else and put all the codings under the if, under the else. Okay. To make it clear, they are directly writing this. Again, finding is greater than or not. So now the temp tens data is 75. 75 greater than root tens data is 50. 75 greater than 50 is true. It goes inside. What I told, once you go inside, you have to check for the null. Once I go inside, I have to check for the null value. Yes, this is false. Okay, it's not equal. It is null. So if will not work, I would go directly to the else. I'll go directly to the else part. So what I'm doing, I'm assigning the temp address to the root right. Temp address is what? 4000. I'm passing into the root tens right. Root tens is right now this one, this field. Okay, so what I will do, I will make this one is null now. Okay, it is null. Okay, and this one is previously it was 50. 50. Let it be 50. And this what? I'm measuring the temp value to the root tens right. So this is 4. So now automatically it's pointing to the right. Now this becomes the